All right. Do you have any questions about homework at all? Yeah. All right. Give me the specifics and we'll do it real quick.
Calculate the per unit length DC resistance for the following wire.
All right.
American wire 6 AWG, solid at 259 by 30.
What's that?
Solid at 259 by 30. Solid and 259.
All right. There's solid's the first one, and then 259 by 30 is the other. Okay. Go ahead.
You got 20 American wire gauge, which is solid at 19 by 30.
And then 20.
Yep, yes, sir.
Go ahead.
That's solid at 19 by 30.
No, it's solid at 20. Then what's the other dimension?
28.
Uh-huh.
30.
Times what?
It's 7 by 36.
Oh. This is 7 by 36. I'll explain this in a second. Is that what it is?
But that's 19 by 34. 32, sir. I'll just forgive the.
Wait a second. Is this right? You want one for just the American wire gauge of 6 and it's solid, right? Is that the first one?
Yes, the first one.
Let me go through this one sequentially. I'll explain the others. All right. You always start with the basic formula. RDC for a wire is proportional to the length, inversely proportional to sigma. And this is going to be DC, right? Just a second. I got that thing on too. I hope it goes off. Yeah. It's DC, and it's divided by, therefore, the cross-sectional area the current flows through. For a round wire at DC, the current is uniformly distributed over the area. So the area is the total area, which would be pi a squared. This is just the cross-sectional area of the wire. Now, the next thing you do, it says solid. And for copper, sigma for copper is about 5.8 times 10 to the 7th, and that's 1 over ohm meters or Siemens per meter, either way. I like to put 1 over ohm meters. You're familiar with the term ohm. Now, after that, the next thing you have to do is figure out what A is. So I posted the actual, for the American wire gauge. Electrical engineers and electrical and computer engineers rarely are exposed to this, but there's both stranded and solid wiring that you have to be familiar with if you do any kind of real design that goes out the door. I can tell you stranded wires work best when you have a lot of bending possible, and solid wires are best if it's permanent. There's no motion. That's my take on this. Solid wires in general are much better. They dissipate heat better and everything like this. With these small wires where you get a whole bundle of them, they can act like fuses and they can burst if you get a transient current sometimes. And if it's localized, then I'll explain more of that as I go. So now you have the table right there, right? When you go in and you look at 6 AWG, it'll have a diameter there, right, in mils. Correct, class? What do you get for mils, the diameter? 162 mils. And that's diameter, mils, and that's diameter. So if you take this 162 and divide it by 2, now you have the radius. We could have used diameter in there, but I like using radius and sticking with radius. Now, this is in mils, right? This is going to be A. We have to take mils and change them to meters, all right, or centimeters. Preferably, I like it changing everything to meters so I don't mess up. All right, so for this, well, Wentworth's book, I think, has this in the back. It's 2.56 times 10 to the minus, oh boy, fifth microns in a meter, and it goes through more and more. But you have your Google, whatever it is, you can just do unit conversion. What's the conversion from mil to meter, or mil to centimeter, either the one? 2.54 times 10 to the minus what? All right. And that'll take you to meters. All right. Once you, whatever that number is, I don't know what it is, if you give it to me, let's do this one, just give it to me. 162 by 2 is 81, and times 2.54. Everybody follow me in this? I'm just getting in meters. 0.002. And that's meters. Remember, meters. Or 2 2.057 millimeters. But you got to be sure about these units. You take that number for A and you stick it here, and now you're going to get the DC resistance for the first one. So for part A, for really solid 6 AWG wire, the resistance per unit length is what? DC resistance, anyway. This isn't a hard problem. It's simply just changing the units. But you got to get familiar with this because in the real world, that's the units that they're going to be put in front of you. Anybody? You asked me this one. Do you have a? You guys have calculators. What do you get for this? Just leave L as 1, right? It's per meter, right? L is 1. Anybody? No? Did you get it?
Is that a 10 to the 7th on sigma?
Plus 7th. Yeah.
0.004103.
Say that again. 0.
0.004103.
That's ohms per meter. Is that right, class? Is it 4.103 milliohm per meter? Is that what the answer? I gave you the answers. 1.3, and this is a DC? Then we made a mistake.
I made a mistake. I didn't put mine.
What's that?
I didn't put mine.
What did you get? 1.3 milliohms per meter. That's solid.
I forgot to put
All right?
That's right.
Now, next, after that, he asked for, is this 259 by 30? By 30, is that what it is?
Yes, sir.
All right, now here's what happens here. Please listen. The 259 is the number of wires. The first number is the number of wires that are in parallel. Because what it looks like is this. You're going to have a whole bunch of wires that are tightly bound, and this is the cross section I'm showing you. So the first number whenever they do American wire gauge is going to be the number of wires if it's stranded. The next number is going to be the actual AWG rating of one single wire in that strand. Do you follow me? Please make sure you see this. You're going to see this again. All right, stranded wires you're going to run into in bundling all the time. Almost all the stuff that you get with Cat5 cable is bundled stranded wire. Lots of other things. Whenever you have electronics with a lot of different IOs and stuff like this, you'll see it all the stranded wire, and it's bundled. Usually, well, it depends. If it's an electromagnetic noisy environment, then they actually bundle this and put a shield on it. Okay? All right, now for this one, for part 2, let me just do this, because this is solid. We checked first one. For part 2, now we've got 259 by 30. So first, for 30 AWG wire, we know the resistance is always going to be per unit length, 1 over sigma pi A squared. We're after the A for 30 AWG, right? If you look at that, what do you see for AWG 30 solid wire? What's the, in mils? Or give me the diameter first. Diameter is what? I put that up there on purpose so you wouldn't have to look on the internet. What is it? It doesn't have 30. Isn't 30 down below there? 30.
30 diameter in mils is 10.03.
10.03 what? Centimeters?
That was in mils.
That's mils. Okay. All right. So that's the diameter. So what I'm going to do is then take the diameter by 2. Now I've got the radius, and now I'm going to multiply that times 2.54 times 10 to the minus 5th. And this will put it in meters. So this is the diameter. Just give me what that number is and then put it in that equation. So we're going to get the R per wire. This is resistance per wire. 0.127 times 10 to the minus 3 meters. Is that right? It doesn't sound right.
No, it is right. That's right. Yeah.
That is right? Okay, if it's right, now we're going to get the resistance per wire. What is this? Just take that and stick it in this equation.
Copper.
Yeah, they're all copper. Unless it says explicitly it's aluminum or steel, you always assume copper for wire. It's used universally, by the way, not just in this country. I just need this number here. 1 over sigma pi a squared.
What's copper?
5.8 times 10 to the 7th. It's right up there. Here, this is the conductivity of copper. You're going to get familiar with this if you're electrical engineers. Electrical and computer. What? 0. Say it again. 2? 3. 3. 8?
Yes.
Go ahead. All right, and that's going to be ohms per meter, right? Correct? Now listen, we've got the resistance for one of these. These are all in parallel. What do if we want the resistance of the wire, braided wire? If they're all in parallel, class? Divide by the number, right? That's all you do. So the resistance for this one per unit meter for the stranded wire, it should be just this number, R of per wire, divided by the number. And in this case, the number is 259. So it's 0.388, or 338 divided by 259. And what do you get for that? 0. Say it again.
0.01306.
And that would be ohms per meter. Is that what the answer is? Is that what it? Okay, good.
What is that under the R next to your radius formula?
This?
Yes.
I just said per wire. It's resistance per wire. But what you always do is look at the resistance per wire and divide by the number of wires with stranded wire. And you have to be really careful when you get high frequency. Here's the real thing that happens. When you're at a high frequency, now the skin depth effects here may or may not become pronounced. Remember, skin depth has to be of the order of the actual radius before you start worrying about AC resistance, right? Now, if it's solid, the skin depth, it may be a high frequency problem if it's solid, follow me? But if it's stranded, then it may not. And that's the thing you have to keep in mind. You always take a look at the skin depth with respect to an individual wire when it's bundled. And if the skin depth is significant, is of the order, if it's less than the actual radius, then you have to default to the high frequency formula, all right, for the single wire resistance per meter. But if it's not, then you don't do it. However, for a solid wire with the same equivalent resistance, DC resistance, all right, a solid one, there, the skin depth, it may be a high frequency problem for sure. All right, if it's, matter of fact, that's the real thing I should say is, if it's a high frequency problem for a solid wire, it may not be a high frequency problem for stranded wire with the same resistance per meter. All right, the reason is you're looking at the skin depth not with respect to all these bundlings, but with just one individual wire. All right, that's the key. Make sure you see that. What's the next one? This is just a turn the crank. I mean, the way I do this, I use MathCAD. The only thing I do is create a little table, general formula, and then I want to raster through these values. It's not very tough to do, and it's just repeated. You should do it just to get used to thinking that way. Another problem? I gave you several.
Determine the frequency where the internal inductance of a 32 ohm wire begins to decrease.
All right. Now, all right. So we're looking for the frequency where it goes from AC to DC, you might say, from where we could treat it as a DC problem, and when we have to treat it as an AC. So first, give me the specifics of the problem.
32 AUG solid wire.
32 AWG solid, right? Solid wire. Go ahead.
And you're trying to find the frequency where the internal inductance begins to decrease due to the skin effect.
All right. Now, inductance, DC, is equal to simply mu 0, or really mu over 8 pi, and that's henries per meter. That's DC, right? The inductance, AC inductance, that's equal to what? LDC, the DC inductance, times 2 times skin depth divided by what? The radius. Do you remember this one? That's the formula I gave you. Wentworth gives you a slightly different version of this. This one's easier to remember, in my opinion. Now, you're trying to find the frequency when all of a sudden this becomes important. And the way you do it is this. Well, there's a couple ways. In Wentworth's book, he's going to show you a graph. I have it. Is this problem out of his book, or is it out of the problems I gave you?
You only gave us your problems.
All right, well, we're going to show you where, in Wentworth's book, he does, Stu Wentworth shows you in chapter 9, I want to show you where it is. If you look at page 504 for a second, in your book, you're going to see a crossover frequency when 2 is equal to A over sigma. Now, let me put it to you this way. When this number becomes 1, when 2 sigma over A becomes 1, that's when you need to start worrying about that, all right? Does this make sense to everybody? Because when it's 1, then it is LDC still. But anything greater than that is going to cause this to go down. Does that make sense to everybody? So what is this going to be? Well, that's A, right? Take A to the other side. Divide by 2 is sigma. Correct, class? Now, sigma is the skin depth, correct? What is the skin depth formula? That's equal to 1 over the square root of pi f mu sigma, correct? I'm just making sure everybody knows that, right? All right, now we're really just solving for that frequency, right? So I'm going to invert everything, and I'm going to say that square root of pi f mu sigma is equal to 2 over A. That's still legit. I took 1 over both sides, correct, class? Now I go ahead and I'll square this side, so I have 2 over A squared, right? And then I divide that by pi mu sigma to find the frequency. And that's the way it's done. In his book, he'll have, I think it's 2A over sigma is the frequency, and he shows it there on page. Anybody looking in the book on that page I gave you? Isn't that what he has there as the point?
For frequency, he's got 4.
No, look down here at the graph. See right here? No, right there.
There.
Yeah. Hey, look at the graph where he does it. So this is A, and this is, all right, so now we got to find the radius. Can somebody give me what A is for a solid 32 AWG in mils, and then we'll convert it to meters. 8 mils? All right, so it's 8, right, divided by 2, 4 mils times 2.54 times 10 to the minus 5th, and that would be meters. I don't know what that is, but
We got 1.016 times 10 to the negative
4.016 times 10 to the minus 4.
1.016.
Oh, sorry. 1.016 times 10 to the minus 4th. So now go ahead and use that number here. Remember, you got to stay with MKS when you use this. Don't put mils in here. All right? So when you go ahead and do that, what do you get? You get 2 over whatever that number is. Square it and divide it by pi, right? And mu is 4 pi times 10 to the minus 7th, and sigma is 5.8 times 10 to the 7th. You probably aren't familiar with this. Most of you aren't familiar. Sigma for copper is about 5.8 times 10 to the 7th, and the units are 1 over ohm meter. I'm going to make a comment about this. There is some discrepancy. There's types of copper that are crystalline, I think it's crystalline, and alloyed copper, where this can be different. So this is for pure copper, and this is a standard thing that we use all the time. Got it? All right, what'd you get for this? For F? Anybody?
megahertz.
1.7. Now, what's the answer? I don't know. What is it?
That's right.
That's how you get it. All right? The whole idea is this. You get the LAC and you set the coefficient to LDC equal to 1. That's the way you always remember this. It's simple if you do it that way. I got to tell you one other thing, too, about this. In this country and Britain, AWG is used for all the wires. In some other countries, they may have a different standard. Now, y'all know how we still use miles, right? And everybody else, if you're on roads in China and other places, it's kilometers, isn't it? Right? There are different standards of measure used throughout. They're usually either System International or MKS or English units. But there's some other stuff out there. I'm just warning you, when you get out in the real world, you're going to see some weird units sometimes. And the way that the units that are weird usually come from measurements that are not standard throughout. For instance, mils is not something you see used but by machinists most of the time. All right? But mils are used nevertheless. It's an English unit. There's other things for weight, and I'm trying to think of some of the examples of this. I learned about this because when you have an international program, like International Space Station and all this, everything has to be standardized. You have to make sure everything that's engineered on there is done with the same exact units, all right, the conversion units. So they almost always default to SIs. Remember that when you're doing problems. ME used to be a nightmare of just unit conversion. I remember, I don't know if it still is. Y'all have had ME? Did y'all use steam tables in here or not? Yeah. All the unit conversions, BTU to whatever, right? Kilowatts, all that stuff. I don't know who taught you, but I used to despise that. Anyway, that's the frequency. Is there any other question about this, Homer? That's basically it, except for now we could do AC, right? If you want to do one AC one, we will. It's straightforward. It's very easy to do. You just have to apply yourself. This is the hardest one because you didn't know about the stranded wire. If you took if you read about American wire gauge, you'd read that, how they demark this stuff. Anything else? Nothing? Yeah.
I'd like to do one of the AC.
All right, give me one, please. I'm trying to move the class along. I've got things in my mind I want to teach. Have you ever been in this building when the fire alarm went off? Anybody? You? That is a noisy thing. I was thinking about how I heard somebody with a hiccup of sorts. I remember the first time that was really loud back in the 80s. Scared the crap out of my class.
Okay, this is a decent one. Determine the resistance, internal inductance, external inductance, and capacitance of a typical ribbon cable consisting of two 28-gauge wires and
Two 28-gauge wires?
two 28-gauge 7 by 36 wires, 2 meters in
Oh,
length,
these are 7 by 36. Go ahead.
2 meters in length and separated by 50 mils at 100 megahertz.
All right. This is going to get a little long, but what's the length on this thing?
2 meters,
2 meters. And separation distance?
50 mils.
So 50 mils here. All right, for this problem, he wants the resistance. When they say resistance of a piece of wire like this, hear me now. They want the resistance of current going down and coming back. So the resistance of basically twice one of the wires. Understand? That's what they want. They're not in parallel, it's in series, because when we deliver power and stuff, It goes down one, comes back the other. So the net resistance is twice that of one of these. Got that, everybody? You got to understand what's going on. Now he wants the AC resistance of this, is that right?
Yeah, 100 megahertz.
All right, so we have a frequency of 100 megahertz here. And now the next thing we have to do is this. We have to take a look at what the radius is of a single wire. Got me on this one? We're going to get the DC resistance, the AC resistance of that. So first things first, these are 36 AWG wires. There's 7 of them. They're 7 by 36. They're bundled together in a bundle that has the dimensions of a 28 gauge radius. All right, so they got 36 gauge wires, but they bundle 7 of them, and that'll fit inside the housing for a 28 gauge wire. Got me on that one? That's the only thing it means. Now, at 36 AWG, that has a certain radius in mils. It's at 5, so 5 mils divided by 2 times 2.56 times 10 to the minus fifth. That will be the radius in meters, right? I don't know what that is, but you all follow my train of thought here? Now, the next thing we have to do is find out what the skin depth is to see if the skin depth is of the order of that or if it's much, much bigger. Got me on this one? So we go ahead, I don't know what this number is, but for the skin depth, that's going to be 1 over the square root of pi f mu sigma. Here, f is 1 megahertz, or 10 to the 8th. Pi, mu is 4 pi times 10 to the minus 7th. And sigma is 5.8 times 10 to the 7th. So you give me this number, and give me that number.
First number is
0.00635, is that right?
It's 6.35 times 10 to the 8th.
I'll do it that way. 6.35 times 10 to the minus fifth. What's this one? Anyone? I had a professor, he could do this on a slide rule and like blink in his eye. I remember using the slide rule years and years ago. If I had to now, if there was a gun to my head, I probably could do it, but it's been a long time.
7.4 times 10 to the negative 9.
Is that right? Look, mu 0 is 4 pi times 10 to the minus 7th. This is, sigma is 5.8 times 10 to the 7th. The 10 to the minus 7th, 10 to the 7th cancel. So this is really of the order of 1 over the square. It's about 1 over 10 to the 4th. This should be like 10 to the 5th, minus 5th here.
6.6 times 10 to the negative 6.
That's more like it. 6.6 times 10 to the minus 6. Anybody confirm that?
Yeah.
You got that? All right. Now, and that's in meters. Now, the first thing you'll notice is what? This is substantially less than this, right? So the skin depth is much less than the radius, therefore it is a high frequency problem. All the current is hugging the surface. Does everybody follow me on this? Now we default to the AC resistance formula per meter, first of all. So we say RAC, I hope you can see this, Allie, back here. All right, RAC is always proportional to the length, right? Listen to me now. What's the length? It's this length plus this length. It's twice the length of one wire. Follow me? Is that 7 meters? 1? 2. Oh, 2. So it's 4 meters, right? Now you divide that by sigma. Really, you can divide it by 2 pi, right? Actually, let me do it. I'll put sigma first because that way you'll get used to this. Sigma is going to be 5.8 times 10 to the 7th. Then it's times the area. This will be 2 pi skin depth up there times radius right here. So you got radius, skin depth, and 4 times this. And this will be the AC resistance of just one wire. Tell me what it is. Remember, not just one. There's 7 of them, so we're going to divide by 7 in a second. Do you all agree with this? Say it again. Well, your eyeball. Just punch it in somebody, please. Calculator's meant to be used. All right, you can do it for fun. I'm tired too, by the way. And looking at you, I get more tired. Not you, him. We have an ongoing relationship along with, where's your friend? Yeah, he's having a tough time too.
that A right there, 6.3 foot?
Huh? Yeah.
I got.
What did you get? Wait. 26.2. Anybody else get this? Thank you. 26.2 ohms. All right? Hear me now. Now, the next thing you do is take a look at how many are bundled in just one bundle of wires. And the number that I was given, there's 7 of them, right? You all see this? First number's the number of wires. Got it? So you divide that by 7 to get the actual resistance. If you divide this by 7,
3.74.
is that what it is? 3.74 ohms. Now that's going to be the resistance of the wire. Is that what the answer is? Y'all understand it's not hard to do this, but you got to be straight in your head because you can make small errors and you get lots of points taken off. Here, exactness pays. Yes?
Can you use 2.56 on 10
That's a conversion from mils to meters. That's, it's 2.54. It should be 5.4. Sorry, my bad.
Well, that's okay, because on the test, I was going to ask, my numbers are near it, but I was just...
Yeah, well, I will give you a conversion. I'm not going to expect you to know the conversion. It's some, yes, 3 feet in a yard, things like that. All right, but 12 inches in a foot. But stuff like this, I'm not going to explain. What else did they want? Any? All right, now, listen to me. For inductance, this is the thing you have to understand. Inductance, once we get the inductance per wire, when you put inductors in parallel, it's divided by the number of inductors. Do you understand that? Now, if there were capacitors in parallel, we'd add them directly. But in parallel, it reduces the inductance. It's not something that's intuitive, all right? But it is the way it happens. So if we're going to do the inductance one, we can do it right here. I think the rest of this stuff you're going to, the capacitance, I can tell you it's just the capacitance between the 2 lines, and I can show you what that is in a second. But if we're doing the inductance, right, let's start, first of all, inductance, and we know we have to use the AC formula. Do you all agree with that? We already know that. So it's going to be LAC per wire. First thing is the length. The length is 2 times the length of one wire because there's return current. Follow me? So it's going to be 4.
I have a question. If you have like 4 wires, would it still just be the return 2? Can you just go through?
Well, when you say 4 wires, you think about differential currents. They flow. When you think about anything plugged in that wall, current flows out of one, wherever what you'd call one of the inserters, and back in, right? 4 wires, how do you want current to be proportioned? 2 of them flow this way, 2 of them this way? Well, then they're in parallel, right? But I don't want to get too far afield from the basic problem.
Yeah, I just was wondering if there was more than 2, just wires.
Well, whenever there's power delivered or signal delivered, it's a differential. All right, there's a plus minus voltage that drives the actual transmission line, if you will. All right. Now, we don't ever send information by common mode. We just don't do that. As a matter of fact, common mode is to be avoided at all costs because it's usually very destructive. And we'll get more into that later. Anyway, getting back to this thing, when we're talking about this thing right here, well, it's going to be 4, right? And then now we're going to put the DC inductance, all right? I'm just going to get the DC inductance. 4 meters, then it's times mu0 over 8 pi. Now that's the inductance, what? Henries per meter times meters is henries, right? That's DC, correct? Now we have to multiply this by the factor involved with the actual AC inductance. And what happens? Then you get what? 2 times delta over A. Don't you, class? I don't know if I had it up here. Yeah. 2 delta over A. And A is the radius of a single wire. Are you with me? We have A, don't we, class? We have the skin depth, don't we, somewhere? Yeah, there's the skin depth. There's A. So what do you get for this? That's per wire. I'm trying to do this methodically, but I want to cover a little something, and we've only got 10 minutes left.
What is that symbol on the bottom for the pi?
This is 8 pi. The DC impedance, DC inductance is just mu0 over 8 pi per, that's henries per meter. Please, I'm trying to make sure that you're clear on this stuff because it's important. Engineers are oftentimes careless right at this point, and they make some colossal mistakes. Well, you'll find this out the hard way usually. When you're running wire harnesses and stuff, if you're getting signaling from like experimental measurements to something that's going to collect the data, and it's not fiber optic, well, if depending on the frequency, it's clock cycle frequencies, you can all of a sudden have a line where the AC resistance is huge, and it becomes the limiting factor, and you're just getting partial data samples and stuff like that. Fiber optic is the way to go if you do measurements. But what do you get for this?
4.157.
4 point what?
157 times 10 to the negative 7.
Minus 7 henries? Is that the answer in the book? Or does he ask for impedance? Does he ask for inductance, AC inductance of the wires?
Internal and external inductance.
All right, this is for one wire, right? Now we have to divide by 7, right? Is it 7? So you divide this by 7, and now you should get the inductance they have. That's per wire divided by 7, and what do you get?
5.9. I got 5.4
Yeah.
Nana. Is that what they have?
Yeah.
Okay. All right. You understand the principle here, right? What's the other thing they're asking for? Capacitance?
External inductance.
All right. External inductance. All right. This is a catch. This is a tricky one. Let me explain this. When they're doing external inductance, what it comes down to is this. Class, we're running late. I got to cover something. Can we take the quiz on Monday? All right? Because I hate to say this, but we're pushing the envelope. I didn't foresee this many questions. I had a lecture plan, but let me go ahead and do this, all right? Did you have a question about this?
Same thing, right?
Well, it's going to be on, yeah, I mean, it's the stuff that we've covered, but I mean, now you're going to get the homework due today also possible, all right? So, because that one, so anyway, just please work with me on this. Are you ready? Work with me. Here, they ask for inductance between the wires, right? External inductance. You have to understand this. This is kind of tricky. We have two wires. They have a separation distance of D from the centers of the wire. You understand that? They have a radius also. These two wires have a radius A. I know there's a bundling of wire. There's all sorts of wires in it, right? But there's a radius of these things, and there's a separation distance between center. Now, please listen to me on this one. When you do internal inductance of wires, the way you could do it, you can, I mean, not internal, but external. You can calculate the total energy created by the magnetic field associated with that current's flowing through those two wires. That's one way, almost impossible to do it here. Or you can do the flux linkage. And flux linkage means how much flux flows in the region between these two wires. And then you take that flux linkage and you simply divide it by current, and that is the inductance. Do you remember doing that in Emag2 class? So this is what you would do, and this is just an Emag2 problem revisited. I can tell you right now, I don't know if you remember this, these are the kind of problems that, you know, I don't know what they put on the FE exam. It used to be called the EIT, Engineering Training. Now it's the Fundamentals in Engineering examination. Most of you are going to take it. This is a typical kind of problem. They always do this. They're basic problems you've been exposed to over and over again in physics and electrical engineering. So they're going to ask for basically the inductance across there. All right, now I know, I'm going to show you how I do it. If I have a current I here, and I'm a distance D from there, or call it a distance rho from there, I know the H field here will be equal to I over 2 pi rho, right? It's in the A phi direction. That's H, correct? If I want B, I multiply it by mu, and now I have B, right? Y'all with me on this one? Now, when I want the flux through the region between the wires, what I do, and I'm going to do this kind of quickly. I had 3 things to cover today. I got zilch. All right, now, when I take a look at this, if this is the first wire, and this is the second wire, all right, I know I have an H or a B field out here from the first wire, right? And I look and I say, if say the current's going up, I this way, coming down, I this way, this is how the separation is. It's D is the separation. So now I want the B field right here at a distance rho. Well, the B field there is going to be the B field from this current, right? And it's assumed infinite, by the way, even though it's not saying it at this, plus the B field from this one at this point. They're additive, by the way. And then you're going to integrate that B field from this and from this over the entire region here, right? Now I can make this case. How many see this? If I just integrate the B field from this wire over this region, it will be the same thing as the B field from this wire over that region. Can you all see that? They're symmetric problems. So I can say the total flux, therefore, and I'll put it here, in that region, sometimes it's good to review this. We know the wire has a length L, and it has a radius A. So the total flux would be equal to twice times the integral. It would be a double integral. And it would be first of the B field from that one, which is just mu I over 2 pi rho. It's in the A phi direction. And if I dotted it with ds, ds would be equal to, call this the z direction. And that's the rho direction. So it would be equal to dz d rho, A phi as well. Now, I'm going to just cut to the chase on this one. The A phis cancel. My integration with respect to z goes from 0 to L. It's going over the total length of the wire, 2 meters. Does that make sense to everybody? My integration with respect to rho goes from, actually it goes from A, right, to what? D minus A. Because you have to account for, if you went from here, because rho is measured from the center of this wire. I've stationed this one right on the z-axis. I can't go all the way over, right, through that thing. I have to say I started at A. Since there's D, well, actually I can go to D minus A, that's right, because D is between the centers of the wire. Do you follow me, class? Now that would be, what is that going to come down to? Well, that's going to be 2 over 2 pi right here, I, then mu. Then it's going to be the natural log of D minus A over D right here. That's a 2 pi there. Then I divide that by the current, just get rid of that current, and now I have the inductance of those two wires, the external inductance. Does that make sense? If you don't understand some portion of this, look it back up in Emag2. It's a straightforward method of doing this. How many remember seeing this? Yes. Yes.
The natural log D over A instead of...
You're right, over A. My bad. Over A. All right. That's the inductance for the capacitance. The capacitance between two wires. Does anybody remember how to get that? You assume these wires are infinitely long. You put a plus rho L per meter here, a minus rho L per meter here. Find the electric field. Remember, you assume Q, right? Calculate E. After E, you get the voltage between here and here. Take what? Charge divided by voltage, you get capacitance. All right. I won't do that now. I wanted to do one thing, if ever. I was trying to cover this. But I'm glad you asked these things, because this is actually, some of this stuff's important to straighten out here. Oh, there it is. So, where we're going with this is we're going to be taking a look at the AC models for resistors, inductors, and capacitors. And I've got to tell you one thing. At high frequency, none of the components I just mentioned look like themselves. They all look like much different animals. And I know this from experience. I do not like working with high frequencies in general unless I have nothing but plastic instruments and I have ceramic kind of clappers and stuff like this, like dental tools, because if you get near that with your body, the actual resonant frequency changes everything. It's extreme. The high frequency stuff is very hard to manipulate or tweak. And it's even harder sometimes to design things. I don't think, do you have a high frequency lab or not, undergrads? Yeah, well, those are always so much fun. I've learned to really despise some of the things we were given to do. All right, now, here's what I want to talk about in the remaining minute or two. We're going to start with what a resistor looks like in terms of a high frequency model. The resistors you're used to are pieces of carbon. They're long, really little logs, right? They're cylinders with all sorts of banding on them that identifies the value. They're carbon resistors that are rated in terms of the wattage and the accuracy. Now, carbon resistors like that are great for breadboards and for doing your laboratory work. In the real world, resistors look like almost anything. In VLSI technology, a resistor is simply a doped piece of silicon that's of the order of maybe 10 to the minus 6 meters in size and scope, all right? They don't look like your thing that's burned in your brain, all right? They don't look like that at all. They look like anything and everything. So remember that. Now, generally speaking, they are identifiable as resistors because of their properties. Now, generally speaking, when you have a resistor, at low frequencies, it better look like a resistor. This is called the lumped element model. You just see this. It's a squiggly line, right? It doesn't say anything about the shape. There's only one thing you have here, usually two. You have the resistance value, then you have the wattage rating of that. Usually those are the two things. You have to know what the wattage rating is because a lot of times resistors are too low wattage. You give me one more second, I'm going to be done with this and I'll let you go. In the real world, here's what happens. Because on a resistor, you develop a voltage difference between there with current flow. You also develop a charge difference, all right? That means there's a real effective capacitance. So normally, you can't get around this. There's some capacitance associated with that. You just can't get around it. You can call it CX the way he does. It means unwanted. You would like to get rid of it, but you can't. You just can't. Now, the second thing you have among here is you have wire. No matter what you do, wire creates a magnetic field if current goes through it. And when it does that, it means it's causing itself to have self-inductance and internal inductance. You cannot get around that. So the way we model it is this. We put an LX here, unwanted, but still there. And that's what really, that's a first order model, I do this with EMC, of what a resistor really looks like. Now, you know the impedance of the inductance is really J omega L, right? And the impedance of the capacitor is really 1 over J omega C. Now just listen to me. I'm going to only do this once. When you think of what goes on in this, you're electrical engineers, you're very good at what you do. If I looked at the resistance between terminal A and terminal B, and I just wanted to plot the magnitude or impedance between A and B, and this is the frequencies. Do this logarithmically. So this is going to be log, let's see, it's going to be log of 1. That's 1 hertz, 0. It looks like a resistor. You keep going on it, up and up and up, and all of a sudden something happens. All of a sudden this capacitor starts shorting out. All right, it starts shorting out the actual, whatchamacallit. The net impedance of this thing now is going to be less than the resistance. It starts shortening out, so it does this. I'll explain. Goes down like this. And normally what they do is on this axis, it's going to be 20 times the log of the magnitude of the impedance. You can just write that down, and I'll explain it more on Monday. You all follow me on this? It keeps going down until it hits something called resonance. You know, because you've had circuits and other things, resonance is the point where all of a sudden the impedance here exactly cancels the impedance here. They're in series effectively. It means you have the minimum value possible down here. And this resonant frequency, by the way, I'll put it down. It's 1 over 2 pi square root of Lx over Cx. Now here's the crazy thing about what I'm doing here. We know that the resistance of this wire is all of a sudden changing once it gets into the range where the skin depth becomes a problem. Follow me? We also know because of that, the inductance value is changing too as you get higher and higher frequencies. So this first order model is just that, a first order model. And this is what you'll see on a scope basically, not exactly. If you look at the Bode plot of this. That's the resonant frequency. Then from here on, it's going to go up at 20 dB per decade. I hear you guys going, just hang on. Now, listen to me, all right? What do you notice about this wire? Well, up to a certain point, this frequency right here, I'm not going to prove it right now, that frequency is 1 over 2 pi square root of RC. That's the first cut frequency right there. That's where it breaks. I can prove it. I don't have time now. But when you see this, there's something that really jumps out at you. If I'm operating with my resistor up in this domain, it doesn't look like it should. It's way out of bounds. And this could be 2 or 3 orders of magnitude. We don't know. That means whenever you're designing something with resistors, and there are possibilities of higher frequency components, you have to take a careful look at the effect of that. I'll leave it there. All right, see you Monday. I apologize for getting... I wanted to do these problems, though, because I knew they weren't in the book, and I just gave you answers.